I want to welcome you all again this evening. Thank you for joining us for this third night of this series. And if you were not here previously, I will tell you just very briefly that my part in this series is to take a look at God's other book. We have begun each of these lessons that I have taught in the book of Romans. So let's begin there again tonight. Romans chapter 1 and verse 20. It's the theme passage for this series. And when I teach this material in a church building, I always want to start with the Word of God, the Bible, which we're convinced is God's revelation. Romans 1:20 says the following, "For since the creation of the world, His invisible attributes are clearly seen, being understood by the things that are made, even His eternal power and Godhead, so that they are without excuse." That passage teaches us, beloved, that by looking at the natural world and examining it, which we're going to be doing again tonight, closely, we can determine these things were made. And if they were made, it points us to the Creator, who is eternally powerful and is divinity. That means not of this world, supernatural. And that's what the Bible teaches in this book. And we could well talk about our Creator just using this book, couldn't we? Because there's plenty of it said in this book, Old and New Testaments. But I have chosen in this series to decide to take God's other book and talk to you about that. So I'm going to set this book aside. No offense to that book, it's God's Word, and you must have it if you're going to know God's will. But you can know there's a God by looking at His other book. So that's what we're going to do again tonight. And this is the third in the series. If you weren't with us for class 1 and 2, I can't spend much time reviewing because there's too much else to do. But you can listen to them. Isn't it wonderful what you can do these days? It's recorded. And it's even, she tells me there's people watching live even as well. So it's incredible. And what a blessing. All right, let's get at our subject at hand. This famous book, Natural Theology, or the Evidences of the Existence and Attributes of the Deity, collected from the appearances of nature, written by William Payne in the early 1800s. At that time, class, and by the way, I meant to mention to you, the elders have given me approval to let me teach this like a class, which means you can answer questions for me and you can participate, which also means you can't fall asleep. And I don't allow that. So thank you, and we're welcome to your class. William Paley's book would have been your textbook had you taken a college class in the early 1800s in Europe, because that was standard. And the whole text of that book, and by the way, here's a reprint of it, a nice new reprint with a nice new introduction. This book is powerful, and you need to read it if you haven't. It speaks of how the evidence of the natural world speaks to somebody who made this. And it's very comprehensive. I'm not going to be reading from that book tonight, because rather I'm going to turn in this direction, because something has happened to this book in our generation. Richard Dawkins has written another book. And he calls his book The Blind Watchmaker. So I'm going to show you what Richard Dawkins does with William Paley. So I'm starting my lesson tonight by a little exposition of Richard Dawkins' book, The Blind Watchmaker. We animals are the most complicated things known in the universe. Does that give you an idea where he's coming from? Biology is the study of complicated things that give the appearance of having been designed for a purpose. That's how he starts. Then I want to turn over here to page 3. We wanted to know why we and all other complicated things exist. And we can now answer that question in general terms. How is it that everybody like us exists? And a lot of other living things. The process by which an airliner came into existence is not fundamentally mysterious to us because humans built it. Would you say amen, class? I think so. What about our own bodies? Each of us is a machine like an airliner, only much more complicated. Were we designed on a drawing board too? And were our parts assembled by a skilled engineer? The answer is no. It's a surprising answer. And we have known and understood it only for about a century or so. The watchmaker in my title is borrowed from a famous treatise by the 18th century theologian William Payne. His Natural Theology, published in 1802, is the best-known exposition of the argument from design. This is Richard Dawkins talking. Always the most influential of the arguments for the existence of a God. And class, that's what I've been using in this series, the argument from design. It is a book that I greatly admire, for in his own time, its author succeeded in doing what I am struggling to do now. He had a point to make. He passionately believed in it, and he spared no effort to ram it home clearly. I want to say it as a result of that quote I just made. I make no apology for yelling. Sometimes I get feisty, if you hadn't noticed. And I say things with firmness and passion. I make no apology for that, because Richard Dawkins and his like absolutely do that, both personally and in their books. And he says, Paley did it too. Look, I passionately believe what I'm telling you, and I spare no effort to ram it home. He had a point to make. He passionately believed it, and he spared no effort. He had a proper reverence for the complexity of living in the world, and he saw that it demands a very special kind of explanation. The only thing he got wrong, according to Dawkins, admittedly quite a big thing, was the explanation. He gave the traditional religious answer to the riddle. He said God did it. The true explanation is utterly different. So class, I want to take just a moment now and pretend you're in William Paley's natural theology class in Great Britain. This is the first thing he would have said to you. And I'm quoting from Dawkins' book, which he quotes from that book. May I use a little bit of British accent? In crossing a heath, suppose I pitched my foot against a stone and were asked how the stone came to be there. I might possibly answer that for anything known to the contrary, it had lain there forever. Nor would it perhaps have been very easy to show the absurdity of such an answer. But suppose I had found a watch upon the ground, and it should be inquired how the watch happened to be in that place. I should hardly think of the answer which I had before given, that for anything I knew the watch might have always been there. That the watch must have had a maker. There must have existed sometime and in some place or other an artificer who formed it for a purpose which we could find actually to answer, who comprehended its construction and designed its use. That's how the class would start. Then he would proceed to tell you this. Every indication of contrivance, every manifestation of design which existed in the watch exists in the works of nature. With the difference on the side of nature of being greater and more, and in that a degree that exceeds all computation. Did you stick with me? And then the rest of the book is an explanation of how nature far exceeds the complexity of any watch. And thus it speaks to a grand designer. Now I'm back to Dawkins. Paley's argument is made with passionate sincerity and is informed by the best biological scholarship of his day. But it is wrong, gloriously and utterly wrong. The analogy between a telescope and an eye, between a watch and a living organism, is false. All appearances to the contrary, the only watchmaker in nature is the blind forces of physics, albeit deployed in a very special way. A true watchmaker has foresight. He designs his cogs and springs and plans their interconnection with a future purpose in his mind. Natural selection, the blind, unconscious, automatic process which Darwin discovered and which we now know is the explanation for the existence and apparent purposeful form of all life, had no purpose. It has no mind, no mind's eye. It does not plan for the future. It has no vision, no foresight, no sight at all. If it can be said to play the role of a watchmaker in nature, it is the blind watchmaker. So that's what Dr. Richard Dawkins, professor of the public information of the sciences at Oxford University, says to you, class. And by the way, similar things are said to your college students in most universities in this world, in their science departments. That, class, is how they say all living things came about. And I have to give you one other quote from this book. In his beautifully written book, The Creation, an Oxford physical chemist named Peter Atkins says it this way: I shall take your mind on a journey. It is a journey of comprehension, taking us to the edge of space, time, and understanding. On it, I shall argue that there's nothing that cannot be understood, and that there's nothing that cannot be explained, and that everything is extraordinarily simple. A great deal of the universe does not need any explanation. Elephants, for example. Once molecules have learned to compete and to create other molecules in their own image, elephants and things like them will in due course be found roaming around the countryside. And folks, that's where this leads. And Peter Atkins is a widely respected physical chemist. And he would write such nonsense as that. You don't need to explain elephants. Once you learn about natural selection and how things can be produced by natural selection, they're just going to pop up. All appearances to the contrary, the only watchmaker in nature is the blind forces of physics. Class, they have such faith in physics and the blind forces thereof that natural selection acting on that can produce everything you see. I say that is the modern day fairy tale, and it's widely believed. So what I've tried to do in this series thus far is to show you that there's some evidence that's been piling up in the last century that says we need to review the argument from design. So that's what I'm trying to do. Brief review from Thursday night. There are three things that have been discovered in the 20th century that ought to make us review this. One is the universe, space, time, and matter had a beginning, and science tells us that. I'm not talking about that particular one in this series. Get my bibliography. Second, the universe, our solar system, and Earth are remarkably fine-tuned to support life. Everywhere you look, class, there are hundreds of factors that are, what did I say, class? Just right. Okay, let's try that again. You're supposed to say with me, just right, okay? What we see is everywhere in this universe, everywhere you look, there are hundreds of factors that must be just right or we wouldn't be here. And that is a fact, class. And it is more abundantly illustrated in the last 100 years than ever in the history of mankind. How do you account for the fine-tuning of the universe that says we wouldn't be here if that didn't happen? I mean, how many coincidences can you add up and say, isn't that interesting what natural selection did over millions of years with the blind forces of physics? I run out very quickly. And the third thing is even the simplest forms of life at the biochemical level contain massive amounts of digital information. Class, there has never been an instance in the history of mankind that information like that obtained in small living things, and all of us, comes without intelligence. It doesn't happen. There's an intelligent source for information. And it's not the blind forces of physics. And that's what we're going to talk about tonight. These simplest life forms, like the one-celled organisms. And I want to illustrate to you what we've learned about these amazing things. Here's what Darwin said. I brought his book with me tonight. Well used, On the Origin of Species. On page 219 of my edition, one of the things I like about Darwin's book is that he spends a good bit of time in his book critiquing his own theory, telling us how we could overthrow it. And here's one. Here's what he said. If it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous, successive, slight modifications, my theory would absolutely break down. I believe, ladies and gentlemen, if Darwin were here tonight, presented with all the evidence you and I have talked about, I would think he said, my theory just broke down. Because natural selection does not work in leaps. As Dawkins says in his book, it's reductionism. If it's too big a leap, you make it smaller. And if that's too big, you make it even smaller. And if that's too big, you make it even smaller. And you get to a small enough leap that nature could have done that by itself. And then you add those up, and you're going to get a massive change over time. That's the theory. And the problem is it doesn't work. So Darwin said, if you can demonstrate for me one complex organ for which you could not produce it by small, slight changes over long periods of time, my theory's dead. Now, one of the problems with this is that the way it's stated, you're trying to prove a negative, and that's very difficult to do. So he was pretty slick in saying it that way. But the fact is, there are lots of them. I presented this one last night. How about the cell? You know what Darwin thought about the cell in the 1850s? He thought it was a glob of albuminous carbon, kind of like a blob. That could have happened by natural causes, just made up somehow by nature doing it. What he didn't know is, look at this. This is what we know. A cell is a self-replicating nanoscale robot. There's all kinds of stuff going on in there. In fact, it has been said about a single cell that it is more busy and active than all the major cities in the world put together. Because there's so much going on in there. There's the nucleus. There's the ribosomes, which we'll talk about a little bit more tonight. There's the rough endoplasmic reticulum. There are lots of microtubules and centrioles. There's mitochondrion. Look at this plasma membrane right here. You see this skin right here? If you blow that up, look what all it's made of. It's got a lipid bilayer and membrane proteins, stuff going through it. We could discuss this thin membrane around a cell for weeks. It's that complex. Why do we call it self-replicating? Did you know, class, that your body divides cells every day? I put a number down here. Now, people disagree on exact numbers, but let me ask you, every day, you want to know how many of your cells in your body divide by mitosis? My references said 50 to 70 billion a day. That means a cell like that divides and makes two cells. I'm going to show you a video of that in just a minute. That means all of that stuff's copied and precisely. You got a new thing that's exactly like the other one. Now there's two of them. And if you didn't, you'd be in big trouble because you got cells dying all the time. You do know that you are a death trap for cells. Your skin, for example, loses thousands of cells every day to death. In fact, the outer layer of your skin, ladies, I'm sorry, it's a bunch of dead cells. Yours feels really soft, but it's mostly dead cells. And you're sloughing them off all the time. That's why I tell kids, take your bath. You want to get rid of those things. But they got to be replaced. And that's done by mitosis, which I'm going to tell you about in a minute. So it's self-replicating because it can reproduce itself. Second, it's nanoscale because it's quite small and can manipulate single molecules. I told you a nanometer is 1/1000th of a meter. That's the level we're talking about here. And finally, it's a robot because its activities are carried out unconsciously and automatically by precision molecular machines that follow ordinary physical laws. And we've learned about most of the molecular machines in the last 20 to 30 years. So my topic tonight is molecular machines. Evolved by natural causes or designed by an intelligent designer? That's what we're talking about. So what's a molecular machine? It's a natural device on the molecular scale with few exceptions made of what class? Yeah. Critically important material, able to convert chemical energy to produce linear or rotary motion, as well as controlling many biological functions. And as you sit there in your body, in your trillions of cells, there are thousands of little machines busy at work. We're going to talk about 2 or 3 of them. Myoglobin is the oxygen storage machine in your muscles. Very important. I'm skipping over that one. It's the simplest one, and the first one we really discovered was a molecular machine. Then there are the kinesin and dynein walkers. The kinesins are involved in cargo movement and cell division, and the dyneins in the beating of cilia and flagella and in cell division, and by the way, lots of other things. And I have a picture here of the kinesin walker. It's this little guy right here. And notice that he's carrying a big old blob. This thing weighs hundreds of times more than he does. This is a little protein here, mostly protein. And look what he's carrying in. He walks along microtubules. And if we had time tonight, class, I would teach you the chemistry that allows him to lift this leg and put it forward. And what happens then that makes the next leg lift up and you move it forward again. We know exactly what's happening to the chemistry of this little machine. And by the way, he is busy doing all kinds of things in your body all the time. If you want some fun, go to your website and find a day in the life of a kinesin walker. It's a cartoon about how a kinesin, how busy he is. It's fascinating. I'll let you do that on your own. But I'm telling you, this little guy's critical to you. And so is the dynein walker, which is even more complex than this one. Tough little guy right there. So, what I want to show you next, class, is in the process of mitosis, the dividing of one cell into 2 exact copies of that same cell. Extremely complex. You tell me, class, when you go study how the mitosis works in a cell and how this massive amount of material is exactly copied, so now from 1 you have 2, you tell me how that came about by natural selection over millions of years, by small-scale changes that add up over time. It's a fairy tale. But it happens all the time, by the millions. So we're going to watch it. And I'm going to show you just a piece of the information. So here we go, class. You're watching here now as this cell and its nuclear material is divided from 1 into 2. You're watching in the pink here the nuclear material. These are the chromosomes. Already the copies have been made. Stop there just a moment. The copies have already been made, so that now you're just dividing it up. Look, we ought to spend a week talking about how you copy the DNA in your system. It's amazing. If you were here last night, I showed you how proteins are built. The copying of DNA is even more complex than that. And it happens at an amazing speed. But in addition to that, all of this cell is divided so that each of the produced cells are exactly alike. Let's keep going. There are processes to this, there are phases, and eventually the nuclear material is separated, the cell wall divides, and stop right there. You have two cells where before you had one, and this one are identical. That in itself, class, is amazing. Looks like the work of somebody that designed this. And that's the most reasonable explanation. Now, we're going to proceed on, and let's watch it again. Because what you've done is just watch what you can see with the microscope. We want now to do the same thing again, only we're going to focus on one chromosome right there. The metaphase, there's a metaphase chromosome. We'll move it up just a little bit and stop right there. You can see, I hope, that there's a copy here and then a copy behind it. Can you see that, class? And they're joined together here. And see these microtubules coming out of each side? Critically important to this whole process. So this is just a little microcosm of the whole thing, because there are 23 chromosomes, right, in you? And they all do this. So we're focused in on one. And I want to show you now what's happening down at the microscopic level. So let's go. So we're going to focus in on this colored area. You know, Drew Barry loves colors. So this is colored red. It's not really red, but it's that because it's active. It's a kinetic core. It's the active place where a lot of these things are happening by the use of, what do you think, class? Proteins, yes. A giant molecular machine that controls chromosome movement. So now we're going to focus in on the kinetic core. And see all these microtubules come out? Those have been built, class, in this process. And stop right there. By the way, they're built. The action takes place, and then they tear up the roads, like any good government. In this case, if they didn't tear up the kinetic core, or those microtubules, they'd have a cell that's so globbed up with stuff they could hardly function. So it has to be recycled. So they tear it up and recycle the material. But that's happening all the time in your cell divisions. How many did I say we had every day? Like 50 to 70 billion. So now I want you to watch what's happening way down at the microscopic level. Let's keep going. The kinetic core is colored red, and what this guy's going to do, Drew Barry, he's going to turn this green when it's time to go. Doesn't happen that way. It's just for your visual appreciation. So lots of things happening here. You see all the activity. The proteins are busy. They're building microtubules. They're getting all the things ready that need to take place in order to make this thing move. And one of them is the dynein and kinesin walkers need to be ready to start transporting things down the tubules. So you see it's turning green now. That means, stop right there just a second. When that turns green, class, that means the molecules involved in this process have said it's time. How do they do that? That's another lecture. But it's controlled by your DNA. Built in by a builder. Let's keep going. So it's time now, and we've got to start this process of splitting up the cell and in particular, the nuclear portion of it. And you see these little dynein walkers going along here? Here's a dynein walker. See how he's prancing along there? Stop just a minute. Can you see he's carrying a glob of things? Guess what you think most of that is? Proteins, different colors, different proteins that have to go this way. There's others going that way. That's the kinesin walkers, and they're walking in the opposite direction. See these little blue guys here? There are very important proteins to help these microtubules stay in place, and everything has to happen smoothly. Let's keep going. The problem with this video, in this case, Mr. Drewberry, is it's way too slow. Because all of that happens rather rapidly. And then eventually what happens back here in the bigger scene is the kinetic core allows the division to take place because of these microtubules and the activity of all those microscopic little things. And they divide, and where you had one, you now have two. But see, you're now privy, class, to the fact that down inside there are all kinds of things going on with machines that are busy making that all happen. None of which could come about by the natural selection acted upon by natural variation over millions of years. Let's talk a little bit about cilia. You know what a cilia is, class? It's a hair. You have lots of hairs on you and in you, like in your nose, in other places I'm not going to talk about. But where's a very important place for you to have hairs that are critically important to your life? Lungs. The lungs. Let me show you a picture here. Your lungs, you see, have an opening here, the primary bronchus, and inside that opening, this is what you've got. Lots of cilia. Thousands of little hairs. First class, you know how you got those hairs? Thanks to Keynesian walkers and Downey walkers that helped construct those little hairs one at a time. And they replace them when they fade out, by the way. And you better have a bunch of them there because it protects your lungs from foreign substances. But they are extremely critically important for life, and they depend on Keynesian and Downey walkers and a whole lot of other things. Wish we had longer to talk about it. But I want to spend the rest of my time tonight on this one. The bacterial flagellum. First time I talked about this, Marilyn said, you lost me in the first 1 minute and I didn't understand where you were going, so make it clear. So class, stick with me. I'm going to be talking about little one-celled organisms of E. coli. Are you familiar with E. coli? Yes. What does it do to you? Well, it could kill you. There are E. coli that are very dangerous. If they find it in your food, they destroy all the food. You remember this? Did you also know that there are thousands upon millions of E. coli living in your intestines all the time? They are part of your biome. And if they were not, you'd be dead. So E. coli is very important to your life and to your death if you let it do so. That's why, class, we've studied the bacterial flagellum of E. coli more than any other creature. Because we've got to figure out how to handle this guy. And he's quite a little creature. And if you all will lift your thumbs up like this and look at them sideways, look at your thumbnail. The width of that thumbnail, you could fit about 1,000 E. coli across the width of that thumbnail. Not very big. That's what we're talking about, class. Are you with me? Marilyn, are you with me? Okay. I'm talking about a real thing that your life depends on. That we have learned a lot about in order to help protect you and to help you. So don't think this is some esoteric subject out here. This is real life. And we have another video. This one is made by a Japanese company, and they're just amazing, I think, in what they've done. Because we're first going to see some bacteria just swimming around. So, and I'll stop right here. Caitlin, hold on just a minute. I got to say a word about Caitlin. I've worked with a lot of AV/IT guys and girls, and she has to be the champion. If you were here last night, we got through that whole thing without a hitch. God bless you. So everybody got to promise me something. You're going to hug her. just for me. And of course I am too. Caitlin, you're doing a great job, and I hope you'll help me on this one, because this is the hardest one. It's not made by Drew Berry. It's a different company. And so I've been to places where they could do the other one pretty well, but they messed up this one. So no pressure, Caitlin. But, all right, so here we go. The first thing we're going to do is watch the little guy swimming. So here's a bacteria. This is not E. coli, but stop right there just a second. This guy has a pretty good set of flagella that's going to allow him to swim around. But this guy's nothing. That's a different bacteria right there. So now let's watch. Here comes the E. coli. See him? Stop. That's a live picture of E. coli swimming around. So imagine now, that's what you have swimming down here in your gut. Am I okay to talk about this? That's live. And the reason he can swim so fast is because he has anywhere from 4 to 10 flagella wrapped around themselves. So they can make it move. Now I want to give you some numbers here, just for fun. Howard Berg, Harvard biophysicist, world-renowned, called the bacterial flagellum and its associated motor the most efficient machine in the universe. It uses almost no energy to do what you were just watching. I don't have time to explain to you how it does the energy piece, but it's based on an acid imbalance. That's how it works. It takes almost no energy. Folks, if we could ever figure out how to build a machine that could function like this guy, we wouldn't have energy problems. But nature's got it all done by the blind forces of physics, of course. The motor class, which I'm going to introduce to you in just a moment, rotates anywhere from 6,000 to 17,000 revolutions per minute. That's 283 per second. Anybody here a motor expert on car motors? Well, I had a guy talk to me about this statistic about the best motors in the Indianapolis 500. None of them touch that 17,000 RPMs. Are you kidding? There is no human motor that touches this. The filament which that motor drives, which rotates like this, goes up to 1,000 RPM, 17 per second, as a result of that motor's revolution. That's just one of them. And the other amazing thing, class, is that rotation, which goes clockwise, can almost instantaneously reverse direction and get up to the same speed, like that. So it's rotating this way about 1,000 revolutions per minute, and almost instantly it can be going this way 1,000 per minute. That's impossible. But I do it all the time. And class, my favorite part, if we had time, is I could tell you the chemistry that has to take place in that little organism for it to change directions. It is a cascade of complex reactions that have interplays and backs and forth that have to be guided and constructed just right, just to make it turn this way instead of that way. And it is so complicated. Don't tell me, you foolish one, that all you need is the blind forces of physics, acted upon by natural selection, which should be God Himself. Let's go on. We're now going to focus in on the animation. This was real live pictures. Now we're going to focus in on an animation. Stop right there. This is a picture of the bacteria, and this is the flagella. You notice there's 1, 2, 3, 4 of them in this case. And you'll notice that the flagellum is connected to the bacteria, and the reason is down inside here is a motor that makes this thing rotate. So my job for the next few minutes is to show you the motor and then make a point that I hope will blow your mind. Remember what we're talking about here. A little creature about 1/1000th the width of your thumbnail that swims inside here that keeps you alive. Let's focus in now. Go, Caitlin. So here we are coming up on the edge of the filament. You'll notice it's connected here. This piece of it, that's called the filament. This is called the hook. Stop right there. Sorry, I made you miss just a little bit, but you saw the filament up there, right? Did you notice it was a different color? That's because it's a different what, class? Protein. Did you notice? Can you back up just a little bit, Caitlin? I'm really putting her to it here now. Just a little bit. Sorry to make you do that. If not, don't worry about it. Is that too much trouble? I don't want to mess you up. Right up there. Can you see that's a different color? And there's another one there, a different color. There are 2 junction proteins required to connect the hook to the filament because it's all different proteins. All right? All right, the hook is very important because it's connecting the filament to the motor down underneath. The hook, class, is a control device. It's a little thing that's exactly 52 nanometers long. It's got the exact right number of proteins in order in a bending shape like that. Absolutely precise. Class, if that thing isn't constructed correctly, it does not work, and this little guy's dead. How does a body build something exactly 52 nanometers long? It's guided by the DNA using proteins. All right, more could be said about that. Let's go on. Down below the hook is the rod, and down below the rod, here the rod goes right up through the middle of this basal body, which is the construction below the cell wall, and we're going to see the different pieces of it here in just a second. There's the rod. There are all different rings. Stop right there just a minute. Here's the inner membrane. Did you notice here, class? This is the cell wall of that little guy. It has 3 layers. Just the cell wall. The inner membrane, it's got the peptidoglycan layer and the outer layer. Very important because the stator here in the middle, which we'll point out in a minute, is connected to the middle layer. But you've got all these rings that are critically important. More about that in a minute. Go on, please. There's the peptidoglycan layer in the outer membrane. Here's the stator. Stop right there just a second. Do you notice that has stobs in it that connect to this inner layer? Class, watch up here. If a motor is rotating like this, do you think maybe it shakes? Of course it does. What if you're rotating 17,000 revolutions per minute? I mean, it could shake that little guy to death in short order. The stators stabilize it, and any rotation motor that humans make always has a stator, class. Well, this little guy beat him to it. He's got a stator, and it's around that stator that the energy imbalance allows it to rotate. Keep going. Down below, you see we have the rotor, which is the motor part of this device. Stop right there. So that's in an introduction to you, and I have a great apology to that motor for the inadequate job I did. But you see, can't you see? This is incredible. Now, here's the part that is more amazing. Little E. coli's divide, split apart and make 2. When they divide, the flagellum and its motor are not in the division. In other words, the new little cell doesn't have the motor and the flagellum. It has to be built in the process. Are you with me? So what we've learned is that the little what's the name I'm talking about? E. coli, has to construct the thing I just showed you from the ground up. Class. Not only does Mr. Dawkins and Darwin and everybody else that's evolutionary have to explain the motor itself, which is a difficult thing. They have to explain how the factory that makes the motor is in that same thing, and it builds it. I don't think you got it. You ought to be falling out of your chair. It's like you have a Ford motor, and you also have the factory that builds the Ford motor in the same thing. So here's what's happened, class, over a period of 20 minutes. The flagellum and its motor are constructed. They're constructed in order like you're building a tower. And the book that Michael Behe wrote called The Edge of Evolution, highly recommended. Shows you it's like building a tower on a college campus. And it does it in an orderly fashion, one step at a time. And you watch. Here's how it does it. Are we going, Caitlin? Okay. The first thing that's constructed is the fly F. Stop right there just a second. The fly F protein forms the M ring, the MS ring, I think it's called. There's exactly 26 copies of a specific protein. Should have had you say that. That is constructed first, class. Go ahead. That's the MS ring. Then the fly G protein, directly underneath, stop, colored not green, but it's there because it's different. Exactly 26 copies of that are added next in that order. Go ahead. Next is the fly M and the fly N protein, exactly 26 copies of each. Stop right there just a second. Added to the base here to form the rotor itself. Then the rod starts forming from the bottom up, class. The proteins now, all of them from here on out, are going to be driven up through the rod to be used at the top one at a time. You don't build the top of a tower before you build a base, right? And in this case, they're specific, what do you think, that drive that thing? Proteins. Keep going. So here comes the rod, and at the top you have this cap that forms. And then the stator forms and connects up to the middle layer here. And then stop right there. That rod cap is made in such a way it can drill a hole through the cell wall. Do you think that's healthy? No, that kills things. Class, when that drilling starts and he drills a hole through the cell wall of that little creature, instantaneously watch what happens. Go. You see that bushing and this bushing called the L and the P rings? Stop right there just a second. Both form at the exact same time to stop up the hole, provide stability, and allow the process to continue. And then that cap is dismissed into the cytoplasm. And guess what? Recycled to be used again because it's a different protein. Then another cap forms right here. Go. This is the hook cap because this is specifically made to construct that hook, which is exactly 52 nanometers long. Stop right there. Can you see how it's adding one piece at a time? Is that beautiful, class? One piece at a time until it gets finished. Go ahead now for just a little bit. Stop right there. That's good. That hook, if the inspector came along, is exactly right. In fact, we would say what, class? It is just right. Precisely constructed. And once that's done, the hook cap is dismissed and recycled. And then, let's watch. Next are the junction proteins. You see the two different colors? Stop right there. You have to have two sets of junction proteins in order for the hook to be combined with the filament. And these are specific proteins for specific purposes. Class, are you getting the idea? The protein at the bottom that form that fly M and fly N cannot work up here. And the one up here can't work down there. And the one up here can't be added sooner than it is, or nothing works. Let's go on. And finally, we form our last cap up here. Stop right there. This is called the filament cap, but there's a better name for it. Michael B., in his book, The Age of Evolution, calls her twinkle toes because she has 5 legs and she dances. And she dances in order to let the filament build in precise shape for 20 to 30,000 protein units of filament. The perfect protein for a filament. Because it's tough, it's strong, and it's constructed in such a way that it's all intertwined and it can whip around and not break. And this little cap guides it all. So I want you to watch. Go. The filament cap. She lifts a leg and the protein comes out. She lifts a different leg and the protein comes out. And can you see they're all going in a specific direction? Each one in its place? Stop right there just a second. I just want to illustrate so you get it. And by the way, it's more like this. Only about 1,000 times faster than that. As she adds each protein segment in order up to 30,000. Now let's watch it. Because see, that's way too slow. Come on, move it. That's more like it. Stop. You remember, class, that's all being guided by down there? Because every one of those proteins are being shoved up through that rod. And guess what it takes to make that happen? Other proteins. Go. And class, those filaments are way longer than the bacteria. But they all are driven by the motor inside there. There are multiple protein processes just there. Class, we've talked about one example. You have 30 trillion, some people say, cells in your body. Each of them has machines doing amazing things. Each protein is complex and suited for its function. I would say designed. And it's interesting to me, you can read in rigorous textbooks where they will say they were designed, and then they'll say, but they weren't. There's the appearance of design. No, class, there is design. And there's a designer that is so massively beyond anything we can imagine. Each machine is highly sophisticated, intricate, dynamic, and elegant, and they are spontaneously self-assembled in the cell. So not only do you have this magnificent machine, you have the driving force that builds it. Following the forces of physics, but not blind. And there are thousands of them in every living cell. So I ask you, class, which is a more reasonable explanation for molecular machines? How about this one? They were produced by the blind forces of physics through numerous successive slight modifications produced by random variation acted upon by natural selection. That's Richard Dawkins' explanation. It's a fairy tale. Or were they designed by a supremely intelligent grand designer? I ask you, class, just with what little you know, which of those is more reasonable? I don't think there's any competition. But I hope you know that the second answer is excluded from the science classroom. And let me tell you why. Because science cannot investigate God. Let's get real. God is supernatural. The only thing science can deal with is nature. So you cannot investigate God with science in any direct fashion. Does that mean, class, that you can't look for evidence in the sciences that somebody designed this? Can you not look for evidence of design? And don't we have it all around us in the natural world? And don't we know what designers that have intelligence can do from ourselves? We can draw conclusions about it. But if you step into the realm and say it's God that did it, you've just stepped out of science, they say. I say, no, you can't do God directly, but you can certainly do him indirectly. And the evidence is overwhelming. So is it reasonable to believe in God in this scientific age? I was told through my college years and on up, you better get over God because we don't need him anymore. Class, we need him more now than we've ever needed him in the history of mankind. It is more reasonable than ever.